Hey everybody, this is Larry. This is me going on Q3 of the bi-weekly Contest 148 longest special path. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. I think the tree part is definitely very tricky, right, to do or possibly to handle, especially kind of this problem. But the thing that which I didn't do on this contest, to be honest, and maybe I should have, to be frank, or at least thought about it more explicitly, is think about it instead of a tree, because basically for this problem, you're just finding a special path that kind of cuts off in a way, right? So the way that I would think about it is think about the linked list case. If you have a linked list, how would that work? The reason why linked list is a little bit easier to think about is just because there's no communication with branches and stuff like that. At least it'll give you an idea on kind of just how to solve it, right? And of course, if you really think a little bit deeper, then the linked list case is going to be like having an array. And if you think about it as an array, then maybe things will come a little bit, hopefully that's the idea that, you can use. Sorry, I'm bringing up the drawing board because, I feel like there is some drawing opportunity here. Okay. So the idea here is that, and we don't have to figure out a tree yet. The idea here is that we have a linked list, right? And here maybe this is too hard to draw, so I'm just gonna think of it as an array, right? Actually, let me move it up, because if you have a linked list, a single linked list, then you can just think of it as an array because we don't add or remove items anyway. So you have an array, you have this element, right? And then the question is that, okay, so maybe you have some colors. Maybe this, let me change the colors since I actually do have access to colors. You have colors in this bucket, and then, and these are like the nodes or whatever, and then maybe there is a duplicate color, and then there's another one, right? I don't know, you get the idea kind of, and I'm having too much fun with this maybe, but that's besides the point. I don't know, it's kind of hard to do this actually, but right, something like that. So then the idea here is that now you are going from left to right, right? And well, what happens when you go left to right? Well, it's kind of honestly pretty straightforward in a way. There are two parts of this problem. One is the length, and the other is the number of nodes. We'll just kind of honestly, my first part, we'll just skip the length part first. But yeah, what if we're just doing the number of nodes? And there's some if statements to change it to the whatever, it's fine, right? Well, then here, hopefully the visualization is just pretty straightforward, right? So we keep track of, from left to right. We go, okay, well, this one we have a length of 3 on 3 nodes. This one, well, here we kind of, duplicate this one. So we have to cut it off, right? So there's a cutoff here now, right? And then now we still go left to right again. And then we go all the way here, and then up to here. Then now this node cuts this one off, right? Because it has the same color. So that's really the idea. And once you have the visualization, especially with arrays, then that's all you need to do, right? And then that means that for every one of these, all we have to do is just keep track of the last element. Keep track of the last element that was there, right? For that color. So here we'll keep track of red, green, blue, and then we look at blue and we're like, okay, well, there's the blue. So now we can update the blue, and also, we cut it off, right? And we do the red. Technically, we also update the red and cut it off. But of course, that cutoff is going to be dominated by this cutoff. So and then update this one. I guess the two greens are different, whatever, right? And then here again, update, right? So there are things you can do, and you just update, and that's it. I think the 1D array problem is pretty okay, right? With one element or nodes, you don't have to worry about the lengths yet. Right, and then how do you get these lengths, right? For example, here, well, it's just 4 nodes because you have 4 indexes. And then the second part is about the second step maybe to think about the lengths, right? Because Okay, I mean, I said you can skip it for a little bit, but at some point you have to solve the problem, which is length. Well, I mean, it is the same visualization, exactly the same. We just have to keep track of the length is in each one, and that's it, right? And there are a couple of ways you can kind of think about the length of each one, because basically the short idea, I mean, the ultimate idea, or ultimately what you want to do is now instead of this thing being the number of nodes, you want this to be the sum of all these elements, right? Where this could be, I don't know, let's say this is 3, 7, 2, 1, and so forth. And if you've seen me do this the last couple of weeks or whatever, you'll probably get this idea already, you know. And here maybe we have some numbers, right? And here you have some numbers, you're trying to get the sum of this segment. Well, what do? Well, what you do is prefix sum, right? So you have to prefix sum, I'm not going to write it out. I'm going a little bit fast because we've been doing a lot of prefix sum problems. My apologies, but the idea here is that, okay, so you have you have an array that keeps track of the sum that is the entire thing, where each interval is the sum of this. For example, this index is the sum of this, sum of this, sum of this, and so forth, right? So that's prefix sum. I'm going fast, my apologies. And so to get this segment, it is just, this segment is just, you go to an originally, just the entire segment minus this segment. And that's it. That's the entire problem. So if you have a 1D array, then this problem is done, right? You have a 1D array or a linked list, really, and how we think about it. So then how do we think about it in terms of trees, right? Well, it's not that different. Right, so here, maybe I'll draw it out. I mean, you get the idea. I'm too lazy to redo the color. But the idea here is that, okay, well, what happens when you traverse a tree? Well, when you get to a leaf, okay, when you get to a leaf, you just pop back up, right? And then you pop back up, and then let's say here there's another branch. Then now maybe you just, maybe I'll draw the branch a little bit cleaner, right? So let's say right here is another branch. So then now here there's another color, you know, and so forth, and there's that, right? So that's really it, the idea. I mean, I'm not gonna lie, the implementation is not as, whatever, you get the idea. The implementation is harder, right? It's not easy, but the idea is what I want to impact you with, or whatever. Just want you to at least understand the idea. That means that, okay, every time we go back up, we pop, and then we want to be able to also keep track of the last thing that's there. For example, if you have a pink coming up, then this should match that one. This is actually purple, I know, but bear with me. Just pretend that's pink for a second. Right, so you have to kind of match that and not maybe match this or anything like that. So there's some bookkeeping and tracking. And then you have to also keeping track of length and the nodes as a tiebreaker and stuff like that. But honestly, if you have the idea, it's, you know, well, we'll go over the code together, so that'd be fine. But yeah. Okay. So yeah. So first we create an edge list, an adjacency list, so that we can actually traverse the table. Otherwise, this is the entire code, which is pretty nice, right? Because the hard part is just the idea. So we do a recursion from the 0th node. This is a very long thing, but we just kind of we're abusing the implicit stack. Yeah, there are ways to, and I actually have an explicit stack on scene and scene node, but yeah. But basically, just to go over it, node is the current node, parent is the parent node, so you don't go up the tree by accident. Scene is actually, so scene sub I is equal to, oh, I put it on the bottom. Okay, scene sub I is a collection, or the sub I is a list, or a stack actually. It's a stack of where the last scene, where the color was last seen, right? Color is I. Current is just to show the current prefix sum for this node from root, right? Oh no, it's not from root, it's No, this is from root. This is from root. This is from the way that I did it. I guess you could have actually changed it if you like. There are other ways to say the same thing, because you don't have to do prefix sum. But I think this way is a little bit easier. Anyway, scene, and that's it for wait. Oh, I skipped one. Last prefix is just the cutoff we introduced in the drawing, right? Basically, that's just the last prefix that we have to kind of, like we cannot go before that because, well, it would match some color in the things that we've seen, right? So that's the idea. Okay, so then there are 3 more variables, but they're just the same thing, really. I even prefixed them, or suffixed them rather, with node. It's just that this is on the length, right? So we care about the length of the input. Okay, yeah. But the node version is just it's the same thing, exactly the same. You can think about the node version as maybe like the length is 1, so it's just a copy of this, right? And the reason is so that we can just do some if statements to get the answer. But yeah, so okay, so let's say you have the parameter defined. Then now we go, okay, if we've seen the color before, then we have to do rows to cut off, right? So this is the cutoff, right? So we update cutoff with last prefix, and then the same with node, right? This is just a update cutoff with node version, right? That's it. Yeah. And then we just keep track of best. I mean, these are kind of defining the problem, right? Best is the longest path, and in those, the one that use the fewest number of nodes, right? So yeah, it's just if statements. And I guess this part is actually something, which is that the current prefix sum, remember we call that current is root to here, prefix sum, right? So last prefix is the prefix sum or prefix sum at cutoff. So then current minus last prefix is just the chunk before the cutoff, right? Or after the cutoff, sorry. Because and the way that I would think about it is that let me bring up the drawing really quick. Is that yeah? If you have something like if you have a node, right? Then and you cut off here, then this only counts for the last chunks, right? Because if you kind of look at this graph, then which is the same as what we drew before, but let's say that we have this as the current variable, and then this is the cutoff. Then that's how you get this chunk. That's basically the idea. Yeah, and again, these are just tie-breaking things. So the node version is the same thing, except for length is equal to 1, more or less, right? Yeah, and then now we traverse again, updating the states. So then for for each node and the length that's in the edge, make sure we don't go to the parent. Then now we just push things on the stack, and you can probably be a little bit cleaner about it, but it's not a big deal, right? But yeah. But I push it on an explicit stack, so both the scene and then the scene with the number of nodes. This is the new prefix sum if we went that path, which is current plus L, which you also see here. And this is the new number of nodes, which is always current node plus 1. That one's a little bit easier to understand. And that's it. That's it. We have the new node, the new parent node, the scene that we updated. We just kind of... In fact, we don't even need to pass it in. We could have put it whatever somewhere else, but it's fine. The last prefix, remember this is updated here as the last cutoff. The new prefix sum, and then the same parameters but for the node portion, right? And then when we're done, we pop, and that's it. Yeah, that's the tricky part. And then we kick it off with with 0 at the root node. No parents, a lookup table for a list, 0, 0, 0, 0, and all these things, and then we just return best. And we call it that when I say length, we just treat it as length is equal to 1. So because the length is actually the number of edges, if it's equal to 1, you just add 1 for the node, and that's it. Best number of nodes. Make it slightly smaller so you can probably even see most. Oh, I had too many comments to see all of it. Okay, fine. Okay, so I barely squeezed in everything in one screen, but yeah. So what is the complexity on this one, right? Well, I mean, we look at each node once. That's it, and we only do O of 1 operations everywhere. So yeah, that's it. That's all we have for this one. Linear time, linear space. This is linear space, but also the stack and also the other actual stacks. So yeah, linear time, linear space, and that's all I have for this one. Let me know what you think. Thanks for watching, and you could watch me solve it live during the contest next. Am I good? Negative numbers don't matter. Yeah, okay. Yeah, okay. Yeah, that wasn't that bad. All right. I hate that in virtual contests you do get to cheat a little bit in the total accept, and I think the leaderboard actually also spoils it for you a little bit, which hopefully I don't. But yeah, because then it kind of gives you a little bit of an estimate of difficulty. But anyway, you try your best. I mean, it is what it is. I should have made it. Anyway, okay, you have a tree stuff, still tree stuff, still tree stuff, weighted tree. You're given integer nums. Nums of I is the value at I. Okay. 0, 1, 2, 3. What? Nums of I. Nodes are colored by the corresponding. No. What? Can you use what? I mean, that's fine. I mean, this is fine, but like, tell us what the colors are. Like, why do they not tell us what the colors are? And then they use a different color for example 2. Like, what does that mean? Am I missing something? Why? What? Yeah, okay. There's always some guesswork. Okay, focus on the problem and stop criticizing me, Larry. Okay. Okay. A special path. Okay, so there's a special path is defined as a downward. I'm taking so long to read because I'm just like being harsh for no reason, and then I'm suffering for the points. Anyway, it's not a big deal. A special path is defined as a downward path from the ancestor node, such that all the rise and node in that path are unique. Okay. Downward path from ancestor. Okay. Note that a path may start and end the same node. Okay. Return away with length of the longest and minimum number of routes in all longest path. What? The minimum number of nodes in all possible longest special path. Minimum number of nodes. What does that mean? Longest special path. Why is this 6? 2 to 5? Oh, I see. Because it's the path. They make you guess a lot of things on this problem, right? Like, I think the thing is that I try to read these without like assuming things, like even honestly, even on words like length and path and the longest and all these things. I try not to make an assumption, because honestly, I made assumptions before and I'm wrong a lot because people write things in weird ways. And here, they don't really talk about paths at all. Or they talk about the paths, but they don't define what the length is, right? I guess you can kind of reason it that it is the sum of all the lengths between the nodes, but they should just tell you, right? Like, this is not, this is about, like, this is not something tricky. This is just about being careful and being polite. Anyway, okay. That's why, because I was reading this as, and especially since the node are now colors, and which is also even more confusing, but that's besides the point. Actually, I guess that part is not that confusing once you know what they're going for, but it's still awkward before you do, and that's why it is the. Okay, Larry, focus. Let's see. So length sub I is 10 to the third. Edge is a tree. Num sub I. So they are could be many unique things. I mean, I think the way that they want you to think is going downwards, right? But I think that's not it, right? That's just an upward and then binary search or something, right? Or repeat doubling or whatever. So from each node, you see how far you can go before you see the same node more than once. And you can even, actually, is that true? Maybe. I mean, you definitely can do it that way, and it'll be n log n. So that's probably fine. If I was good enough to implement that, that would be n log n. But is there an easier way? Or more reasonable way? It is going to go upwards anyway, right? Do I really need to do whatchamacallit? Binary lifting? How would binary lifting work? Because the merge is you have to figure out the unique, right? So every node you could build off in dynamic programming. So going up, or maybe from the root down, you build out, you pre-process it. There's this node we haven't seen before because there is this property. Maybe you don't need. Okay, so let's say you're going from the root down, but you're going from the root down to calculate node up. Does that make sense? Yeah, I think that's fine. You just have to be really careful, I guess, with the states, and you have to be really careful with the states, and then you just kind of almost like a weird sliding window, right? But everything is unique, or they have to be unique as a part of the invariant. That's fine. All right, let's go. It's just that for search, right? Yeah. I mean, it's very easy to get wrong though. But you know, that's why we get paid the big bucks, so that you could get wrong on get it wrong. But the thing is that when you pop, so you have to do another prefix sum e kind of thing from the node. Actually, it's just that for search with bookkeeping, I think. I think the other stuff is too clever. Let's just go. We have the node. It's rooted at 0. Okay. So we still kind of need to parse it. Okay, so it's rooted at 0. Whatever, let's call parent. And what do we care about? We care about all the nodes that we've seen, and then a sort of the prefix sum on top of the stack, on the core stack. And the question is and it's annoying, but it's doable. Okay. So maybe a scene array or a scene set, and then Okay, and then the last prefix or something. I don't know. Naming is tough. Okay, I think we're Gucci. Maybe. No, we're okay. We're okay. We're okay. We are okay. And then the current count. Have to be careful, but we're okay. We know dot. Okay, we'll fill it in later. Okay, what are we trying to do here, right? Then now, let's just calculate this thing first. So if node or num sub node, which is the color of node. Actually, I like to call it color because that's really what it is, right? I'm surprised they didn't do it that way. I guess, I don't know, whatever. The color of node, it's in scene. Then we want to update color of node. Nope. Color of node is scene. Then previous, we want to update the previous by yeah, and then just have to be really careful, I think. Scene color of node is equal to current, because that's just the prefix sum at that level, right? And then at the very end, okay, we said, oops, previous equal to none. If previous is none, then we set it back to none, which means it's a delete. Else, then now we set it back to the previous. And that's really it. Okay. Scene, we can pass then. Last prefix is the last prefix we care about. So if we have seen this color, then we have to update last prefix is equal to max. I like to do f max. Last prefix and then the current. Yeah, and that's just to keep track of the prefix sum. This is the last. Current is the current prefix sum, and last prefix is the last prefix sum in which we haven't seen. Well, that's from the last color that we see, right? So okay, so then now you have the new last prefix, which is fine. We update it. And then the new current, which is going to be current plus L, right? I guess I forgot the L. And then now we just have to update best. I think this is roughly right. I mean, I think maybe I have to be a little bit careful somewhere, but we'll just have to keep track of nodes. I'm just going to focus on lengths for now. The nodes will be easy. It's just the same thing, really. We just have to keep track of more variables, but this is going to be this is going to be linear time anyway, so it's fine. Yeah, okay. Just have to do an array, not a matrix. Let's see if it runs. I know I don't update best, but I just want to make sure that it runs. Oh, I guess we have to update this no matter what. What? What? Yeah. Okay, now we have to update best. Do we want min or longest path? Longest path, right? Okay, so if best is less than current, then current is here. All right, let's see if that's good enough. Actually, I don't know why I just didn't do it. 11 and 8. Well, that's definitely not right. Can we even get 11? 5. Oh, I guess we can get 11, but the reason is because 0 and 2. So the 2 should have cut off the what should the length of 6? Oh no, no, oh, the nodes. Okay, I'm confusing the nodes with the edges, but okay. So that means that, okay, so maybe I have to do the math a little bit differently. Also, this is just really wrong because this is not current. It's current minus last prefix. Why else would I do it? I'm just being sloppy. 6 and 0. Okay, so that's actually right. So we were just being a little bit silly. And then we just have to do the count of the nodes, which we just have to keep track of, right? Last prefix is length, and current is equal to current length prefix, and then we just have to do last prefix node for nodes, which is kind of awkward, but that's fine. Technically there's one, no, 0. What are you doing? And then the current prefix is, yeah, same idea though. Last prefix node is equal to f max last prefix node current node, yeah, and then now this is last prefix node current node plus 1, and then else if best is equal to current minus last prefix, and current node minus, what is it called? Well, last prefix node, but are we minimizing or maximizing? Minimum. So okay, so if this is less than best nodes, best nodes is equal to current node minus last prefix node. So let's make this -1. No binding by best node, so best, should be singular anyway, but I was just kind of a little bit confusing. -1, oh, because I don't return it, because that's the best way to not get a right answer. Okay, so it's doing infinity. Oh, in this case, we want best node is here. 0, 1 is wrong. 6, 2 is right though, but why is 0, 0? Oh, it has one node. How do I change it? I'm not even that confident about this being right, frankly. But or the node part, because I didn't really think about the edge cases. Okay, so well here we already have 2 nodes, so we should start at 1. Maybe, I don't know. Prefix sum, okay, but that, okay, so you go from 0 to 1. I guess prefix is 0, is that right? I don't know. This feels like a hack anyway, so I don't know. Current node minus, this should give me the right answer, right? No, it's just wrong. Now I'm dealing with edge cases, maybe. Okay, let's think, right? Why am I wrong? I mean, you're wrong a lot. Previous. What am I doing? I'm not updating something. I'm not updating current node. Like, what is previous for again? The previous prefix sum? We don't use it. Why don't I use it? That's why I'm getting confused. Oh no, because we maintain stuff on scene. I'm so confused. Am I just lucky? I mean, what am I throwing up here? Scene is the current prefix sum. Because we see it, then now that means that this isn't right. This is off by a little bit. This doesn't make sense. Because this shouldn't be the last prefix. I mean, well, this should be last prefix, but it shouldn't be current. This should be the previous value, right? I think the 6 is just a little bit lucky. But luckily, the other parts are not. So we have to keep track of it. I don't think this is right. Okay, I think the idea is right, but the bookkeeping is not right. Because there's a reason why I use this, which is that we have to keep track of the prefix sum. But somehow I'm getting lucky with the example 1 that and example 2 really. But the example 2 is kind of crappy, so maybe that's just designed to be that way. But because if it's seen, then that is the last cutoff. Because this doesn't make sense. The last prefix should not update to current. That doesn't make sense at all. Something is way wrong here. The idea is right, but I'm bookkeeping terribly. That's why I did all this work for a scene, but okay, so last prefix that we care about is either, okay, so we do. And then now if, of course it's always going to go to current, because current is bigger, but this established the next thing, which is the previous one, right? Yeah, no, this should really be previous. I don't get why I would, and here I just kind of copied and paste, so this is definitely wrong. But this should give us the right answer if that's the case, which we're not seeing, right? So okay, so let's print out some statements. So we have a node, we have last prefix, and the current prefix. Maybe that's all I need to kind of debug. Maybe 0, 0, 0, node 1 is 2. Okay, last prefix is 0. That's fine. So the 2, if it all goes right, should set the last prefix at 0, which is not right, because we don't want to subtract from that, which is reasonable. We actually want to get it from the next node after that. That's why current was right, because it's previous plus plus the node that they care about. I mean, that's why current was right for this example, is because it happens to be the next one. But this is not right necessarily. Because basically this is the prefix sum of all the nodes including this one, but to get the prefix sum of the next one, you need the next node. So actually, this should be here, and maybe one plus L. Okay. Then as a result, everything is kind of messy. But that's fine, maybe. But this last prefix is wrong too. Oh no, now it's right because it adds in the edge. Maybe. Okay, but it doesn't think that way though. 39. If previous is none, then we update scene to be because scene is a stack in this case. Okay, fine. So if we don't need the previous, well, maybe we do. It's easier to write, I suppose. Okay, and then now we can pop, and here we push, and then we pop. I thought that before we were using an implicit thing, but yeah, this is not a pop anymore, right? And we pop whenever we push anyway, so even though it's more. Okay, so now I think we're right, actually. We just have to fix it for this one as well. So we have seen, we have, you know, we always want to be seen, right? But we need a scene node. I think that's it. And it's the same idea. Maybe, if it's right, I don't know. They should be matched anyway. Previous node. Well, I guess this one is easier because it is just everything is just +1, but hopefully this is right. Oof. No, that's fine. Am I off by 1? Maybe I'm off by 1 because you start with 1 node. Am I off by 1? Nodes are always so tough. I always miscount it. Because I always miscount node and edges. That's why I'm a little bit uncertain, but I think this fixes it. But it's still because you always have 1 node anyway. 0 is not a possible answer. Is there a -1 answer? No, because this is the default answer. Okay. Am I confident? Honestly, not super, but I feel like we're okay. Let me double check the code real quick for any super silliness. Whatever, YOLO. Okay, good. All right, Q4. Yeah, thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, my explanation, everything in between. Stay good, stay healthy to your mental health. I'll see y'all later. Take care. Bye-bye.